Hello everyone, my name is Chowdhury Jawaad and I'm working alongside Michael Wanek, and today we will be presenting on a very fascinating and crucial topic in the realm of modern technology: big data analytics for IoT networks. This presentation covers the core concepts, methodologies, challenges, and future perspectives of integrating big data analytics into IoT networks. I hope you enjoy. Thank you. First, let's begin with an overview of IoT networks. The Internet of Things, or IoT, encompasses the network of interconnected devices, such as sensors, software, and various other technologies that communicate and exchange data over the Internet. For example, smart home devices like thermostat and security cameras, wearable devices like fitness trackers and smartwatches, and industrial sensors that track temperature and pressure in factories, all fall under the IoT umbrella. The significance of IoT lies in its ability to provide smarter, more efficient solutions across different fields, leading to increased productivity, enhanced security, and overall convenience of users. These IoT devices are becoming very prevalent in today's society. For example, many of our homes have smart technologies integrated. So many people have a smart blinds system, for example. With the press of a button, the the vertical blinds in their windows are, either closing or opening, and the users can set this based on the time of day or even temperature. Um, Other smart devices like the thermostat that we talked about, those send live data to our cell phones, letting us know, what the current temperatures are, and the user has the ability to set certain temperature ranges during the duration of the day. So maybe the AC will get turned off when it is not being in use, so there's no one in the house, or versus it will get turned on, when people are at the house. So all of these smart sensors are getting integrated into our homes, and it's very accessible in today's time. Moving on to big data, which refers to extremely large data sets that can be analyzed computationally to reveal patterns, trends, and associations, especially relating to human behavior and interactions. Big data is characterized by the 5 V's: volume, the sheer amount of data; velocity, the speed at which data is generated and processed; variety, the type of data, including structured, unstructured, and semi-structured; veracity, the trustworthiness and quality of data; and value, the ability to extract useful information from the data. In the context of IoT networks, the vast amount of data produced by various devices need to be analyzed through big data techniques to gain valuable insights and make informed decisions. Let's delve deeper into the components of big data analytics for IoT. The first step is data collection, which involves gathering data from various IoT sensors and devices. This data is then stored efficiently in systems like cloud storage or data lakes. Next comes data processing, which can be done in real time for immediate analysis or through batch processing for large data sets over time. Data analysis involves applying techniques like predictive analytics, machine learning, and data mining to understand the data and extract insights. Finally, data visualization plays a crucial role in presenting these insights in an easily understandable and visually appealing format. Data collection is a fundamental element of big data analytics for IoT networks. It begins with IoT sensors and embedded systems that gather data from the environment. This data is then transmitted through various network protocols, including MQTT, CoAP, and HTTP, or message queuing. Telemetry transport is a lightweight and efficient messaging protocol ideal for IoT applications with limited network bandwidth and power. It operates on a publish-subscribe model, ensuring reliable data transmission even in constrained conditions. CoAP, or Constrained Application Protocol, is specifically designed for use with constrained devices and networks. It uses UDP for transport, making it low overhead and efficient, much like HTTP, but tailored to the needs of IoT. HTTP remains in use due to its widespread adoption and compatibility with existing web technologies. Though not as lightweight as MQTT or CoAP, it facilitates easy integration with web services. However, data collection in IoT network faces significant challenges. First, scalability is an issue. As the number of devices increase, so does the volume of data, requiring robust and scalable systems to manage it effectively. Second, there is a challenge of managing diverse data types. IoT devices generate various data formats, necessitating versatile storage systems capable of handling structured, semi-structured, and unstructured data. And third, ensuring data integrity is crucial. This means maintaining accuracy and consistency throughout its lifecycle. Data can be corrupted during transmission due to network issues or malicious attacks. Implementing encryption, regular validation, and secure transmission methods are essential to protect data integrity. In summary, IoT networks collect data through sensors and embedded systems using protocols like HTTP. Overcoming challenges related to scalability, data diversity, and data integrity is vital for effective data collection. This ensures that we can fully leverage big data analytics to uh, derive meaningful insights and enhance operational efficiency. When it comes to storing the massive data generated by IoT devices, traditional SQL databases may not always be the best solution due to their structured nature. NoSQL databases such as Apache, Cassandra, and MongoDB are designed to handle unstructured and semi-structured data more efficiently, making them ideal for IoT applications. Apache Cassandra is known for its high availability and fault tolerance, while MongoDB offers document-oriented storage capabilities. Additionally, the Hadoop Distributed File System (HDFS) provides scalable distributed storage. Cloud storage solutions such as AWS, Google Cloud, and Microsoft Azure also play a significant role in storing IoT data securely and scalably. Data processing techniques are crucial in handling the vast amounts of data generated by IoT devices. Real-time stream processing tools like Apache Kafka, and Apache Flink offer minimal latency and allow for immediate insights by processing data as it arrives. On the other hand, batch processing tools like Hadoop and Apache Spark are suitable for analyzing large datasets in chunks, ideal for historical data analysis. Edge computing brings the computation closer to the IoT devices, reducing latency and bandwidth usage by processing data at or near the source.
Regression analysis is a powerful statistical method that helps us understand the relationship between variables. In the context of IoT, it allows us to predict future values like sensor readings, energy consumption, or traffic flow based on historical data. For example, analyzing past temperature data from a network of smart thermostats, regression models can forecast indoor climate patterns and help optimize energy use across buildings. On the other hand, time series forecast takes a more dynamic approach by focusing on trends and patterns over time. It's particularly useful for IoT systems that continuously generate time-stamped data. Think about a smart city where sensors track vehicle counts at intersections. Time series forecasts can analyze daily and weekly traffic trends, anticipate rush hour congestion, and inform adaptive traffic signals, ultimately improving urban mobility. Together, these tools turn raw IoT data into actionable insights, while regression explains relationships and predicts outcomes based on variable dependencies. Time series forecasting captures temporal dynamics to model the behavior of systems as they evolve. As IoT devices continue to grow exponentially, harnessing these methods will be key to smarter infrastructure, more efficient services, and better decision making across industries. First, we have supervised learning, which is used for tasks like classification and regression. In the IoT world, supervised learning helps systems make accurate predictions based on labeled data. For instance, a smart thermostat can predict the ideal temperature for different times of the day, ensuring comfort while saving energy. Next is unsupervised learning, often used for clustering and association tasks. Unlike supervised learning, this method deals with unlabeled data and finds hidden patterns or groupings. In IoT, this is especially useful in smart cities. Imagine thousands of traffic sensors spread across an urban area. Unsupervised learning can cluster regions with similar traffic flow, helping city planners optimize traffic light timing patterns. So, together with machine learning models, give IoT systems the ability not just to collect data, but learn from it, adapt to changing conditions, and make intelligent decisions in real time. As we continue building a more connected world, the synergy between machine learning and IoT will be crucial to making that world smarter, efficient, resilient, and responsive. As we navigate through the world of Internet of Things, one challenge becomes increasingly clear. IoT generates massive amounts of data from sensors, connected devices, and embedded systems. But data alone isn't enough. To truly harness the power of IoT, we need to make sense of that data. This is where the importance of data visualization comes into play. Data visualization simplifies the complexity. It turns overwhelming streams of numbers into clear visual formats that help us quickly identify patterns, spot anomalies, and gain meaningful insights. For example, a smart factory generating thousands of temperature and vibrations readings per hour would be nearly impossible to analyze without visual tools. But with a heat map, a plant manager can instantly see which machines are overheating. We have powerful tools and platforms at our disposal, such as Tableau and Power BI, allow us to create dynamic dashboards that update in real time. D3JS, a JavaScript library, gives developers the flexibility to build custom visualizations tailored to their unique IoT ecosystems. These tools make it impossible for both technical and non-technical users to interact with data meaningfully. Let's consider a few examples. Line graphs, pie charts, heat maps. In the IoT era, visualization is more than a nice to have, it's a necessity. It bridges the gap between raw data, actionable insight, helping businesses, governments, and individuals make smarter and faster decisions. IoT is not just a buzzword, it's a revolution that's reshaping the world around us. From the cities we live in to the farms that feed us, IoT is creating smarter, more efficient systems that improve lives and streamline operations. Today, I'd like to highlight four key sectors where IoT is making an especially profound impact: smart cities, healthcare, industrial operations, and agriculture. In smart cities, urban populations are growing rapidly, and with that comes increased pressure on infrastructure. IoT helps cities become more livable by optimizing traffic flow, reducing congestion, and lowering emissions. For example, smart traffic lights adjust in real time based on vehicle flow, while smart meters manage electricity use to avoid blackouts and reduce waste. The result, a cleaner, safer, and more efficient urban environment. In healthcare, IoT saves lives. Wearable devices like smartwatches monitor heart rate, blood oxygen, and sleep patterns, transmitting data to healthcare providers. This can be used for patient monitoring and to make predictive medicine possible. Industrial IoT is transforming manufacturing and heavy industry. Sensors embedded in machines continuously track performance, temperature, vibration, and output. This enables predictive maintenance, fixing a machine before it fails. It reduces downtime, improves worker safety, and boosts operational efficiency, saving companies millions while keeping production running smoothly. Finally, agriculture, where IoT is driving what's called precision farming. Sensors in soil measure moisture and nutrients, while drones and satellite assess crop health and weather patterns. Farmers can make informed decisions about when to plant, fertilize, and water, leading to better yields and more sustainable practices. It's technology helping us grow more food with fewer resources. Across each of these sectors, IoT is more than just a set of gadgets. It's an ecosystem of data, connectivity, and intelligence. And when used wisely, it has the potential to solve some of the most pressing challenges that we face. As cities grow, so do the challenges that we face: traffic congestion, air pollution, energy demand, and infrastructure strain. With IoT, we have new tools to face these challenges. For example, Barcelona's Smart City Initiative. Barcelona stands as a global leader in smart city movement. The city has implemented a wide range of IoT technologies to enhance street lighting, waste collection, and public Wi-Fi. But one of its most impressive achievements is in its data-driven management of traffic, air quality, and energy. By deploying IoT sensors throughout the urban area with real-time data on vehicle flow, pedestrian activity, pollution levels, and electricity usage. Data collection is only part of the story. The real analytics come from big data. All of this sensor data is aggregated and analyzed using advanced algorithms to uncover patterns and predict future trends. Pollution sensors allow for quick responses to dangerous air quality levels. The results are measurable. Barcelona has seen a 30% reduction in water usage, improved traffic flow, and energy savings. The city has become more livable and more sustainable and more responsive to the needs of the residents. This is the future of urban development: smart, connected, and data-driven. As we move forward, embracing IoT in city planning isn't just an innovation, it's also a necessity. Power and potential of IoT, one thing becomes very clear. Data is the heart of it all. Billions of devices are constantly generating information, but to turn this data into meaningful action, we need big data analytics. However, as we scale up our IoT networks, several challenges arise, challenges we must address to fully realize the promise of a connected world. For example, data privacy and security, data quality and scalability. First, data privacy and security. With all this sensitive data, locations being transmitted, health information, health metrics, and personal identifiers, it's crucial that we protect it from unauthorized access. A single data breach can compromise not only systems but public trust. Data quality is also a necessity. IoT devices often spread across diverse environments and networks. This means inconsistent connectivity, hardware malfunctions, or environmental factors can lead to incomplete, outdated, and inaccurate data. So maintaining the accuracy and consistency of collected data is non-negotiable. Finally, there's the issue of scalability. IoT ecosystems expand, connecting everything from traffic lights to industrial machinery. Systems must be able to process, store, and analyze massive data sets in real time. Addressing these challenges isn't just about keeping up, it's about staying ahead, because the success of IoT doesn't depend only on how much data we collect, but on how well we manage, protect, and learn from that data. Internet of Things is in every corner of modern life, and data privacy and security have never been more critical. Each of these processes and sensors transmit massive amounts of data and includes highly sensitive information and can leave significant threats and vulnerabilities. Therefore, data breaches where malicious actors gain access to sensitive information, there's also the danger of sensor hacking, where attackers take control of devices to manipulate or disrupt observations. Privacy invasion occurs when personal or location data is collected without proper user consent. There are many mitigation techniques such as encryption and anonymization, and therefore we must implement robust access control mechanisms. As IoT becomes more and more pervasive and transforms our industries and everyday life, it is our responsibility to safeguard this data. As we continue exploring the evolving world of Internet of Things, it is important to consider the future of big data analytics for IoT, AI convergence, edge computing, and enhanced data integration. For example, artificial intelligence becomes more advanced, it becomes tightly integrated with IoT systems. AI helps us analyze the massive volumes of data generated by IoT in real time using raw input into insights and predictions. The combination of AI and IoT supercharges decision making and allows systems to learn and adapt continuously. The second trend is improved edge computing. IoT devices can send this information to the cloud for processing. Also, enhanced data integration techniques allows modern analytic solutions which can integrate different techniques to merge this diverse data into unified real-time dashboards. In summary, we explore the importance of IoT networks, big data analytics, and components and use of IoT, such as traffic optimization in smart cities. There are also critical challenges, such as data privacy and system scalability. There are future trends such as AI convergence, edge computing, and enhanced data integration. Therefore, the importance of big data analytics cannot be overstated. It is the engine that transforms raw data into decision-making power. The future of IoT and big data will be shaped by continued innovation as technologies evolve. So too will our ability to harness data for sustainable growth and resilience and smarter living. Thank you.